Hi, welcome to Principles of Energy. This is Module 7. We're going to be talking about photovoltaics and a little bit about solar power and how we make electricity using that power. And to start off, we're just going to begin with the electrical engineering equations of just figuring out how much power you have in a system, and I'll show you quickly resistance. Now, if you want to go into this in more detail, there is a math walkthrough showing you how to calculate the power in various solar systems for solar cells and solar structures. And obviously, if this is going to be your major, you will be taking electrical engineering courses where you'll go into things like Ohm's law in great detail and so on and so forth. But we'll do a quick graze over of that topic so that you get your feet wet on the subject matter, and then we'll move on to photovoltaics. So starting out with just a little bit on symbols, and what you'll see, if I'm calculating the voltage of a symbol within there, I will see V in my equations. When I'm going to look for a current, in my symbol will be I. I will be equating for power. Power will be in the unit of watts, and my symbol will be W. And then resistance in flow will be signified as Ohm's law, which is symbolized by an omega. So a little bit on the quick table. I love these triangles. Pretty much they show you that the equation for trying to figure out different actions. So if I want to know resistance of power, because it's a W over here, so my resistance and power, I would do a volt times a volt divided by the ohm, which is the resistance in the power. If I want to know the power and I have amperes times the amperes times the resistance and power. And if I want to know my wattage total, or my total amount of power, and this is the standard equation, which would be power P is equal to my current, my I, times my voltage, my V. So P equals I times V. Another version of all of those in symbols. And as I said, there's a math walkthrough. This is a quick practice example. I have a math walkthrough to walk through these. So now let's talk a little bit about photovoltaics. And before we get too far in there, I'm actually going to flick over and I'm going to show you a video that I couldn't link through YouTube that I want you to see to help you understand just a little bit about how the solar cell works. And then I'll start talking a little bit about photovoltaics, and then you'll see some pictures of my own home. So without further ado, let me flick over.
The primary piece of equipment for generating electricity from the sun is the PV module, more commonly referred to as a solar panel. These are actually formed from a number of photovoltaic cells, often shortened to photocells or PV cells. A PV cell is, in very basic terms, a large diode, a one-way device for electric current. They consist of two different layers of chemically altered or doped semiconductors to form an anode and a cathode, separated by a junction, which is a very thin insulating material which has two electrically charged.
I'm going to just stop really quick because as much as I like this video, there is a little mistake in the video. Notice that they have the cathode and anode are correct in their symbolism here, but where they've named the semiconductors are wrong. This should be the P-type conductor up here, and this should be the N-type conductor over here. All right, so continuing.
Surfaces, positive on the cathode side and negative on the anode side. The junction only allows electrons to flow in one direction. When an electron, which is negatively charged, approaches the junction from the anode side, it first encounters the negatively charged surface and is repelled. But when the electron approaches from the cathode side, it first encounters the positively charged surface and is attracted. If it has enough energy when it approaches the junction from the cathode side, the electron can cross the junction to reach the anode layer. Thus, electrons can move relatively easily from the photocell's cathode layer to its anode layer, but they can't go back. When a PV cell is exposed to particles of light, known as photons, some of the photons are absorbed in the diode's cathode layer. Some of the energy absorbed will be transferred to electrons in the cathode, giving the electrons the energy required to cross the junction and reach the anode. But once the electrons have arrived at the anode, they can't return to the cathode directly across the junction. Instead, they must flow through an external circuit in order to return to the cathode. As the electrons flow through the external circuit, they can give up some of their energy obtained from the light photons to devices in that circuit. The construction materials of a PV cell determine how effective it is in different light conditions, and also how expensive they are to produce. The most common form of PV cells are manufactured from silicon and are either classified as a form of crystalline, thin film, or a combination of these two technologies.
All right, so you'll notice that I jumped ahead a few slides, just a little bit about the history of solar cells, talking about it was an invention of the Bell Laboratories, and that invention has skyrocketed in today's, but originally when it was first premiered in the 50s, it wasn't really seen as a viable resource, and it took NASA to adopt it and really develop it more, and so on and so forth moving forward, and that's where it lands us to today. Which leaves us off to where the video was mentioning that we like to use silicon. And the reason why is silicon is highly adaptable. It is in the metallic family, and therefore it has a metal bond. The metal bond means that it's sharing electrons easily. Sharing of electrons easily makes it an easy substance to create electricity from. You also noticed in the video that they were talking about magnetism. The things that are the same, like the negative approaching the negative, are going to repel one another, and the positive approaching the negative will be attracted and therefore be able to do what's called jumping the band gap or the junction within the structure. At the end of the video, they mentioned that the silicon can be poured to be crystalline, or it can be poured as a thin film or gel. Now, gels are weak in their metallic structure. You think of a solar calculator and the little strip that makes up the solar calculator, or the cheaply made solar toys that you can get at a store where something does like a little hula dance based on solar energy. Those are gelatin pores. If you really want to create a lot of power, what you will do is you will pour it at high heat and allow it to form a crystalline pore. And a crystalline pore has a very specific frequency of band gapping, which I will get into in a few slides, that allows for it to respond to certain spectrums of light. Spectrums of light like we were talking about back in Module 6. So once again, here is our cell, and I don't need to go into the P and N type silicon, how it's flowing through the system. What happens when light strikes the cell? Electrons are knocked loose from the atoms in the semiconductor material. They approach the junction. The negative electrons that have been knocked loose are allowed to jump the band gap, knocking more electrons out of the substance below, and that allows us to create an actual electric current. And so my current is a constant flow. Once again, electricity is electrons jumping from one valence shell to another. There is some categories of PV cells. The cell itself, which is the silicon pore, which has its N and its P pores on top of one another. So one is electron depleted and the other one is electron rich in its substance. That can then be placed into a module, which is circuited together, and the module can then be placed into an array. And this is where we think of the entire panel, right? So a module is circuited itself. Now with an array, the array can be multi-circuited. So each panel can be circuited on its own current. This way, if I'm shading half of my system, if half of my system is shaded, the other ones will still produce power, where if I only shade out one half, the power will pitter out in the system and never reach the line. So on that note, I'm going to pick up with the part 2 video.